Hello, my name is Sajant Anand, and I am a physics graduate student at UC Berkeley, and I'm a guardian for the Quantum Physics and Materials Science Interest Group. Today I want to tell you about some recent work done in collaboration with the quantum computing team at IBM on getting accurate results from a noisy quantum computer by making it worse. So this should sound counterintuitive, and hopefully by the end you'll understand why this is a reasonable thing to do. Why by making my computer worse, I can actually get better results. When people typically hear of quantum computing, they think of this image in the background of something inside a dilution refrigerator that's cooled to really, really low temperatures. And this is in fact the technology that IBM uses. I, however, am a theorist, so I actually don't work with quantum computers directly. Instead, I just work on classical computers doing very large-scale calculations and try to understand what is actually going on behind the scenes. So, to begin with, let's just try to come up with an abstraction of a computer that can be used to describe either quantum or classical computers. So when I say computer, what I really mean is something just takes an input, so in this case x, performs some function on it specified by the computer or the program that you're actually trying to run, and what it outputs is just f of x, so just a function applied to that input. And that's what I'm going to describe as a computer. So in particular, let's consider classical computers. Our input, so our input and output, our data, so x and f of x, are just going to be binary numbers. So zeros and ones, and you can have as many of these binary digits as you'd like. And currently available, on your smartphones or on your computers, you have between billions and trillions and more of these bits just freely available. These are really now cheap and easy to produce. We started in the 60s with maybe 1 bit, and now we're up to billions and trillions of bits. So it was a very quick advancement in our technologies. On the operations side, what we can actually do is just binary arithmetic. So given 2 bits, we can either multiply them or add them. So an example is binary addition of 1 plus 1 is 0, again, because we're doing mod 2. Additionally, we have this great feature of being able to copy data. So if I have a value in 1 bit, I can place it into another bit. This is most commonly thought of in terms of like some programmatic notation. If I have one variable x, I can just create a new variable y by assigning y the value of x. We do this all the time. On the quantum side, things are a little bit different. So we work with these things called qubits, or quantum bits. These are quite spoken of quite a bit. And really, these qubits are just a superposition of 0 and 1. So I'll describe a little bit more in detail what a superposition is, but really it should be thought of as a fundamental difference from classical computing. Bits are either 0 or 1, and these quantum bits are, in some sense, somewhere in between 0 and 1. And the number available these days is between 50 and 400 at companies like IBM and Google. So really, depending on the actual technology you can use, you can have anywhere between 50 and 100. And typically at universities around the world, you can maybe have 2 to 50 of these qubits. So we're on a much, much smaller time scale. So despite the fact that people have been working on quantum computing experimentally for now about 30 years, we've gone from 1 qubit to 400 qubits, let's say, in 30 years compared to 1 bit to trillions of bits in 60 years. So there's a little bit of a different time scale where it's much harder to scale up in this quantum side than the classical side. On the operations, the quantum operations are specified by these things called unitary gates. Unitary is just a classification of a type of matrix, and the actual details here are not really all that important. All that is important is that quantum operations need to be reversible. So if I do a quantum operation, I need to be able to undo that same quantum operation. And in particular, this unitary condition, or this reversible condition, actually means that I cannot copy quantum data. This is a fundamental limitation of quantum mechanics. So if I have a quantum piece of information, I cannot create a new variable storing the exact same piece of quantum information, right? There's no copying. This makes things fundamentally harder and really is a root cause of why we're having so much of a harder time making quantum computers scale and bringing them into commercial fruition. So let's talk about what makes quantum computing special. And in particular, there's 2 things: entanglement and superposition. So really, these are the two key crucial features that actually make quantum computing significantly different than classical computing. So let's start with superposition. So typically, I'm going to denote my states by here with these angle brackets. And really, you can just think of this as meaning some quantum piece of information. So I have 2 basis states, 0 and 1. These are the typical bits, my zeros and ones. And here, with this Greek letter psi, I'm going to denote a quantum state on a single qubit. And what I'm going to denote it here is just as a superposition, really as a linear combination of my 2 bit basis states. It's a linear combination of 0 and 1 with some particular cofactors. So immediately it looks like if I have 0 here and 1 here, my quantum qubit psi is somewhere in between 0 and 1. It's a superposition. It's not exactly 0, it's not exactly 1, it's somewhere in between. And oftentimes it's really easy to visualize this in terms of these two angles, theta and phi. So if I imagine that I have my 0 at the top of this sphere, so this is just like a ball, and a 1 on the bottom of the sphere, the point is that a quantum state can take any state on the surface of this sphere. And I'm talking about a pure quantum state. So the point is, bits can be either 0 or 1, and quantum states have access to a whole bunch of, really an infinite number of other states specified by these two angles, theta and phi. Okay, so that's one difference, superposition, is that you don't have just 0 and 1, you have some complex superposition of the two. And the second is entanglement. So for entanglement, let's just consider I have two qubits, which I'm going to represent by these dots with these lines through it. So these are two individual quantum states. And I'm going to say that they have this quantity known as entanglement between the two. And it'll be clear what that is in just a second, denoted by this red line. So qubits 1 and 2 are entangled. And then I'm going to do an operation here, denoted by this lightning bolt on qubit 1. I'm going to do some action on qubit 1. You can think of this like applying a gate, or like doing some operation on a computer on one of the two qubits. And the point of entanglement is that if these two qubits are entangled, then by doing an operation just on qubit 1, I can actually change the outcome of qubit 2. So I can change the state of qubit 2 even though I don't act on it at all, just by acting on something it's entangled with. So to give you an example of this, let's just say I have two variables in my quantum computer, x and y. And these two variables are entangled, x and y are entangled. Then just by acting on x alone, let's say I add 2 to x, that'll actually change the state of y. This should be, counterintuitive. This is not how classical computing works. If I have two separate variables, they're separate, right? I can't act on the other one. I can't change the state of the variable without acting on it. What I'm telling you is entanglement is fundamentally different, where if I have two qubits that are entangled, acting on one can change the state of the other, denoted here by a measurement. So I'm going to measure this second qubit, and the outcome will actually depend on what I did to the first qubit. And the point is that this actually does not depend on the distance between the two qubits. So regardless of the distance L between the two qubits, an operation on qubit 1 can affect qubit 2. And this is what led to Einstein determining entanglement, or calling entanglement, spooky action at a distance, because regardless of the distance between these two, acting on one can have an effect on the other. And Einstein termed this spooky action at a distance. So these are the two things that make quantum computing special. Entanglement, the fact that I can act on one qubit and have an effect another, and superposition, that my individual pieces of information are neither 0 nor 1, but instead some linear combination of the two. So now that you know a little bit of what makes quantum computing different, the natural question to ask is, why should you care about quantum computing? What really makes it different? Are we going to solve the exact same problems that we already solve with our computers today? Hopefully not. The goal of building a quantum computer is that we should be able to solve fundamentally new problems using these new devices. So Richard Feynman, a visionary in this field, has this great quote saying that nature is quantum, goddammit, so if we want to simulate it, we need a quantum computer. So that really inspired, I would say, this one big thrust of the field, is that if you want to study some quantum mechanical system, you should really use a quantum computer to simulate it. And a quantum mechanical system can be anything from electrons interacting in a 2D plane, as I'm trying to show here, so each of these are electrons, they're moving in some direction, I want to ask about their properties, to more, industrial relevant problems such as the interaction between molecules and drugs. If I want to study how a particular molecule binds to the outside of a cell, ideally I should try to incorporate some quantum mechanical effects into this. If I really want to do that accurately, I should use a quantum computer. So if I have some quantum system and I want to know its properties, it'd be great to use a quantum computer. Another option, application that people get very excited about is in optimization. So if I have some really, really hard optimization problem, maybe I can use quantum computers to get around some difficulties that we know of for classical computers. So for example, a classic one is the traveling salesman problem. So this is saying that a salesman needs to visit a number of different places, and each of those places is spatially distant. The question is, what is the optimal route that salesman should go to visit each of these places at most once, such that the trip is the cheapest, or he has to travel the least distance. This is known to be an NP-hard problem, meaning that it is exponentially hard, at least we believe. We currently do not have any algorithms that can solve this problem on a classical computer in anything less than exponential time. Now, it's not immediately clear that quantum computers will be able to solve these efficiently. It's just there's hope that maybe we'll be able to use the increased power of quantum computers to address these kind of problems. Okay. So, now I've told you what makes quantum computing special. I've told you why you should want to do it, but now I need to tell you why these devices really don't exist. Or if they do, they do exist, but they're really only confined to laboratory experiments at this point. So, what makes quantum computing hard? Well, the first thing is that operations are really not perfectly accurate. So imagine I want you to add two numbers, 2 plus 2, and let's suppose you go to your calculator to do it. You type in 2 plus 2, you're going to get 4 every single time, right? There's no ambiguity of here. Again, you can do it on paper, but the point is that the computer doesn't make a mistake. This is a little bit different than for quantum computers, where actually, if I do the most basic quantum operation, I actually can get the wrong answer. Even if I know, if I know just analytically, I can write down on paper what the answer should be, the quantum computer can make a mistake because the operations themselves are probabilistic. They're not guaranteed to work. So this is a concept known as fidelity, or quantum operations are going to be characterized by this fidelity, which tells you how close the produced output is to the ideal output. So I put in two numbers, I apply some function to them, I get an output, and I ask, is this output actually correct? And current estimates say that the 2-qubit fidelity, for example, from IBM last year, is 99.9%. That sounds pretty good, 99.9% is pretty high. We essentially take that to be 100%. The issue is that now, when you consider doing a bunch of these operations, even this tiny bit of infidelity, this tiny bit of error adds up over time. So let's consider the following example. Let's say I have 100 qubits in a row, and I want to do 100 layers of operations. So imagine this sort of picture. It's like people call this like a brick wall circuit. And then I have my qubits laid out this way, and each of these is just going to be some 2-qubit operation. I'm not going to specify the operation, but this square just says I'm going to have these two qubits interact in some way. And the point is I'm going to do 100 layers like this, right? So this is what I call a 100-layer circuit, and that each of these is a layer and it interacts neighboring pairs. I'm going to do this 100 times. Well, the fidelity is going to be the total fidelity of the output of the circuit is going to be estimated by the product of the fidelity per gate. And the fidelity per gate, let's say, is going to be 99.9%. The total number of gates I have to do is 99 times 100. 99 gates per layer, and then 100 layers. So that's 9,900 total gates. So if I just take this fidelity per gate and raise it to the power of 9,900, I actually get a total overall fidelity of 10 to the minus 5. So intuitively, this is saying that if I do this circuit, my answer has an overlap, or is 10 times 9 to the 5 as accurate as my true answer. So it's not very accurate at all, you would think. That my produced answer from the quantum computer is quite far from the exact answer I should expect. So it's hard to know what the actual true answer is because I'm just getting so far away from it. Because each of these operations, although they're quite accurate, are fundamentally noisy. And therefore, if I do a bunch of these noisy operations in a row, I'm going to get a low confidence in my output. So a natural question to ask is there actually any information in the output of a noisy quantum computer if the fidelity is so low? Like, we do all of these operations, each of them is a little bit bad, and after we do this a bunch of times, the errors accumulate, and I don't know if I can trust the results anymore. And this is really one of the fundamental problems of quantum computing, is that we have 100 qubits, and you can consider actually doing this sort of experiment on a Google computer or an IBM quantum computer of taking 100 qubits and doing 100 layers. We just don't know if we can trust the results. So the question is, what can we do to actually get some confidence in the results we're getting from a quantum computer? So to do that, I want to introduce this concept of zero noise extrapolation. So imperfections of a quantum computer are going to be called noise. So I'm going to use noise to be a catch-all term for any imperfections of my quantum device. Any things that are causing it not to give the answer that I expect. So the question we like to answer is, given a noisy quantum computer, which are the ones that we have today, can we extract accurate results? And the result of this work that I want to tell you is apparently so, using a concept known as error mitigation. So I want to explain a little bit of what error mitigation is, and then also put some qualifiers on this apparently so. There's a reason why I'm not being too definitive yes or no. And the idea with error mitigation is ideally what we want to reduce the noise of a quantum computer, but we actually can't do that, right? This is very, very difficult to do, and in fact, people are working to reduce the noise, but this will be a multi-year, multi-decade process. So the question is, what can we do now, today, to get accurate results? And what we can do actually is increase the noise. So now I need to tell you why increasing the noise or making the calculation worse can actually make it better. I do want to highlight that this idea of error mitigation or zero noise extrapolation is not a new idea. It actually was proposed maybe about 5 or 6 years ago by researchers both at IBM and otherwise. It's just that this work that I'm doing currently with IBM is one of the first demonstrations that it actually is a useful concept and something that can be done experimentally. So let's go back to our abstracted model of a quantum computer, or really just of any computer. I have some input x. I want to apply some function f to it, but additionally, because my computer is noisy, the noise is going to operate as some additional function g, and the output is going to be, let's just say, g of f of x. So it's my true output, just with some noise function applied to it. And I want to assume that this noise here depends on some unknown parameters, a, b, and c, with the point being that this g is not some completely random operation, like the noise has some structure to it. If the noise is completely random, I'm not going to be able to do much. But supposing that the noise actually has some structure to it, which it turns out it does on these actual devices, there's some hope that we can actually extract some useful information. So, given this noisy quantum computer that produces this noisy output, what do? The general idea is that if we can characterize the noise in operation, meaning if we can understand the noise on a quantum computer, we can controllably increase the noise, so make the noise worse, but then extrapolate backwards to the noiseless limit. So let's give an example of this. Suppose I make a plot like this. I have my abstracted results on the y-axis, and I have my noise level on the x-axis. The goal is to get to the zero noise level. That is the true result. That's the thing we're actually interested in, but our actual device is going to be the noise level 1. So ideally what we do is just build better and better devices, and the noise level would go down, but that's going to take 10 years or so. Or, it's always going to be 10 years away. So what can we do now is, instead, controllably run the experiment increasing the amount of noise. So if I understand where the noise comes from, I can actually make the noise worse. So first I run the experiment at base level noise level 1. Then I turn up the noise controllably and run the experiment again, and I get a new worse result at noise level 2. Then I do it again at 3 and again at 4. And the point is now, I fit this data to some theoretically motivated function, and I find that if I do this, I can actually estimate what the true value is at noise level 0. So I don't know what actually the answer is, but I'm going to estimate it wherever this extrapolated curve lies at noise level 0. I'm going to say, okay, this is my current estimate for the noiseless results. So here's this Z&E zero noise extrapolation recipe. I learn a noise model for my quantum circuit, G of ABC. So this is essentially saying I want to learn how my noise model depends on these parameters A, B, and C, and so on. I then want to run the circuit controllably increasing the noise, which means I want to choose some values for A, B, and C, run the circuit. I then want to increase my values for A, B, and C, so make the noise worse, but in a controllable way, and then run the same circuit and do this again and again. And this gives me, these different noise levels. I then want to extrapolate the noisy results to the noiseless limit, which you do here by this blue line, and you say, okay, here's my estimate of the true value. And this is really suggested first, in this. There are a few papers, I guess, in around 2016, and some more recent work that actually goes into making this a doable procedure. So the natural question is, okay, I can do this. It seems like a well-defined procedure, but is it correct? Like, there's no theoretical reason that I've given you so far as does this actually work on a current quantum computer? So what I'd like to do now is tell you about some recent work and an ongoing collaboration led by these two experimentalists at IBM to actually demonstrate that this procedure does in fact work on their current quantum computing device. So, generically, given some quantum circuit, it's really hard to verify the noiseless prediction, right? This is kind of inherent. If I could tell you what the noiseless answer is, there'd be no need to do any of this, right? The point of doing quantum computing is that I can't predict the output of the quantum computer on paper or using a regular computer. And I'll get to that a little bit on the next slide. So to begin with, let's just actually consider something that's entirely trivial, a very trivial experiment, which is saying the function I want my computer to do is essentially doing nothing, but it's doing nothing in a very complicated way. So consider this function here, just f of x. It's a bunch of multiplications, a bunch of additions, but the point being is that if you just multiply all these things out, actually f of x is just equal to x. So you give it an input, and it gives you that exact same output back. But it's getting about that by some complicated fashion. It's doing a lot of operations just happen to cancel, right? So that means that on paper, I can tell you exactly what the output should be, because I know what the input is, but there's a lot of internal operations that need to go correct if the computer is going to give me that correct output. And on the quantum side, essentially what we're going to do is these Trotter steps are really just a measure of how complicated the circuit is. And we see that the point being we're going to choose a circuit so that every 4 Trotter steps, the circuit is just the identity. Meaning that every 4 Trotter steps, nothing is done on the quantum computer, I just go back to my original input. So if I start with an initial value that is 1, every 4 steps I should get back to a value that is 1. So let's consider these green dots here. This is what is called the unmitigated, or you can think of noise level 1. I just run the experiment directly on the quantum computer, I measure what I get, and I see that as I make the experiment longer and longer, essentially I can think of it as making this function more and more complicated. My results get worse, as they should, because I'm doing noisy operations. So even though f of x should always be equal to x, I'm making mistakes in the internal operations and I'm not getting back to x. Okay? So that's to be expected. But now let's look at these mitigated results where I do this extrapolation, where I run the experiment multiple times, making the noise worse and worse. And I actually find out that regardless of the circuit depth, I get back to something that is a pretty good approximation of the true answer of 1. So even though here I'm losing a lot of information, I'm able to actually get back to something that approximates my true result. In particular, we're doing this on a device with 127 qubits, so this is actually one of the largest circuits that's been run in the literature. So it's a quite exciting result that we're able to do this non-trivial procedure of taking an incorrect answer and converting it into an estimation of the correct answer. But so far, everything I've told you is for these trivial circuits where really nothing much is going on, right? It's kind of a contrived problem that I've designed a problem so that I know the final answer. Can we actually do this on a realistic problem? Yes, but I need to tell you just a little bit more before I can get to those. And then the question is, suppose I actually want to consider a generic circuit, not something that's just f of x is equal to x. I want to consider something a little bit more complicated. Well, to really do this, I need to be able to estimate what the true answer is. And it turns out that getting a true output, the true answer of a quantum circuit is exponentially hard on a classical computer. So let me tell you why. So given a single qubit here, I need 2 parameters a and b because my qubit is a superposition of the 0 and 1 state. So I need these 2 parameters a and b. Okay, so that's okay. I can represent any qubit just by keeping track of these 2 numbers a and b. Now if I want to represent 2 qubits, I can think of this as just like the outcomes of 2 possible coin flips. So I can have 2 zeros, 2 ones, or 1 of each. And the point being, now I need a separate parameter for each possible outcome. Okay, that's only 4 numbers. That doesn't sound so bad. But the point being is that the number of numbers I have to keep track of scales exponentially with the number of qubits that I have. So a general quantum state can be represented like so, where I have a superposition over all possible basis states of zeros and ones. So to think of this is that I take n coins and I flip them, and then the outcomes are all the possibilities that I can have. Right? I can have up to n heads, all the way to n tails, and everything in between. And that's in total 2 to the n different possible states. So what I need to do is keep track of this, which is just a notational way of representing these 2 to the n numbers. And just to drive this point home is, let's just say I consider 10 qubits. Well, then I need 2 to the 10, or 1,000 parameters. That's just a small fraction of a gigabyte. That's nothing. But you go to 25, 40, and you start seeing that, okay, now I need 4 gigabytes. Oh, now I need 10,000 gigabytes. That's starting to be something. And the point being that if I just go from 40 to 41, I can double the amount of memory that I need. So this is an exponential growth sort of problem. So even though I can do 10 qubits and up to 25 qubits pretty easily, as soon as I get to 35, 40, that's incredibly hard. And the point is, doing 1 additional qubit makes a problem twice as hard. So this does not scale at all, right? We can't go really past. Very few computers on Earth have access to 20,000 gigabytes of memory. So this is really a very difficult problem to consider. Well, a lot of what I work on is actually this idea of tensor network states, which I'm really not going to get into, but I just want to give you an intuitive picture. And really, these are just an entire subfield in theoretical condensed matter physics that really boils down to just controllable ways to compress quantum information. So to give you some intuition behind this, just consider I have this really high definition picture that's 8.9 megabytes. And I can both tell the large scale details and I can zoom in and get some pretty nice low level details. But let's say I want to send this over the web, or I really want to get a really, really large picture. Maybe the amount of memory scale is too much, so what I want to do is compress it, and to say that I want to keep large scale information, so I want to be able to still recognize that this is a flower. But if I zoom in, I might throw away some information that I don't care about. Like, I don't care about getting every single pixel correct. I just need the large scale details correctly. So this is the idea of compression. I can go for some really, really detailed description of this picture to some less detailed description of the picture that's a lot less in memory, but yet still retain all of the most important features. And tensor networks are really just a way to do compression of quantum states. It exactly does this. I want to keep the most important features that determine physical properties. I want to throw away a lot of the fine-grained, short-distance details that, I may not be able to keep track of. So a lot of what we do in the group is develop these tensor network methods to actually study these quantum states on classical computers. So finally, let's consider this error mitigation now for a generic circuit. So this is a circuit that is not trivial, such that it never actually, the input returns the output. This is a sort of circuit where I actually have a very hard time predicting what the final answer is. What we show here is, again, we're really changing some parameter of our circuit. So we can think of this as changing some parameter of the quantum operation that we're trying to do. And at these 2 points of 0 and pi over 2, it turns out that this circuit is exactly solvable in the sense that I know exactly what the answer should be. Right? It just boils down, there's some simplifications in the circuit that I can tell you on paper what the answer should be. But the point being, in between, there's no known answer. So we don't know what the exact answer is. And this is where our group at Berkeley came into play for this project, in that we were asked to really calculate what the expected answer should be in between these two points of 0 and pi over 2. So this is what we did. We essentially calculated what this what the value should be, and again, I'm not getting into detail of what this value is, but just as we varied the parameters of our quantum circuit, we wanted to estimate what the answer should be, and it turns out, in very particular circuits that we've ran, we can actually exactly tell you what the answer should be. So this is very particular to this circuit, but it gives us a very good testing platform. So again, just to walk through some of the details of this, again, in these green dots, we have the unmitigated experimental result. So this is just running the quantum circuit with noise level 1. And in these blue dots, we have the error extrapolated result. So this is, again, running it with increased noise levels and extrapolating backwards. These two colored lines are these tensor network approximations. So the best tools that we have available classically at the moment to estimate what the output of this quantum circuit should be. And in the gray line, we have the exact result that is only available because this is a very specific circuit. And what we find is that the extrapolated results essentially agree exactly with the exact results, which is very, very surprising. We find that despite the fact that these circuits are generic and have no nice properties, we're still able to exactly recover what the output should be, even though the quantum computer is giving us noisy results. These two different tensor network methods, MPS and ISO-TNS, are just really two different approaches that we're developing. The first one has been in the works for about 30 years now, and the second one was developed at Berkeley about 3 or 4 years ago by my advisor, and we're continuing to work on it. So the punchline of this is, does zero noise extrapolation actually work? And the answer, again, is apparently so, with an asterisk. And the second conclusion is tensor network states don't, again with an asterisk. We're going to just explain a little bit of why we actually need to put these asterisks there. The first is that I know that zero noise extrapolation works in this case because I have access to the exact answer. But I only have access to the exact answer because I chose a relatively simple circuit to work with. If I go, again, this is still a generic circuit, so the exact answer is not known in general, but if I go to much harder circuits, I actually don't have access to this black curve at all, so I don't know what the exact answer should be, and in that case, I can't say definitively whether or not this zero noise extrapolation works. I can only offer evidence that it does, but we don't know for sure that it does. And secondly, it's a little bit unfair to claim that tensor networks do not work because I'm not really making an entirely fair comparison. In the quantum experiment case, I'm doing this extrapolation where I get to do multiple runs of the experiment and use the noisy runs to produce an estimate of the noiseless result. But I don't actually get to do that in the tensor network case. I'm just running the circuit once, and I'm saying, here's my estimate given my current classical computing capabilities. There is hope that we can actually make algorithmic improvements to the classical approaches, these tensor networks, to actually reduce the discrepancies between these. And that's something that we're working on now. So just to conclude, and maybe to give you some optimism for why you should care about quantum computers, is that Quantum computers are a nascent, powerful tool that will offer new insights into physics, chemistry, and optimization. They really are a fundamentally different way of approaching problems than classical computers. But unfortunately, noise in operations make the native results, the ones you get just from directly running a quantum computer, they make these results unreliable. So we need to do something else. Option one is to build better quantum computers, which obviously we're trying to do, but that takes a while. What we're showing in this work is that this technique of zero noise extrapolation actually allows you to recover an estimate of the noisy results just by making your quantum computation actually worse. So by making our results worse, we can actually get an estimate of the true answer, which is quite surprising. And in future work, we actually want to think about how we can make classical improvements to our algorithms to actually bridge the gap between these tensor networks and the quantum computer, and really ask, can we incorporate this zero noise extrapolation into the classical simulations? Can we do multiple classical simulations, making each of those simulations worse and worse, and then use that to extrapolate backwards, and therefore recover the quantum results? That is really something that we're super excited about now. Thanks.